Hello class, this is CSE-4600, section 62, week 11, so this is week 12, fall 2024. So, this is the video that I intended to put out last Friday, but did not get the chance to do so because of family things. But here we are now. We are now looking at memory. So, things are gonna get a little bit interesting here. So far, we looked at processes as these things, these entities to which we allocate resources to, as things, as entities that are executed on the CPU, but like one at a time. And now, we're gonna see what processes do, or what happens to a process at the level of memory. So we've seen processes. We've seen what happens to processes when they're on the CPU. We've seen what processes do when they're asking for resources. Now we're going to see what processes do when they're in memory. So, this is chapter 3 of the textbook, well, though there is some information from the other operating systems textbook. You'll know what I mean when I'll bring it up when we get to it. Alright. So let's begin. Programmers like their memory to be abundant, cheap, and non-volatile. That is, when we turn off the computer, anything that is stored in main memory is lost. We call that volatile. Non-volatile is basically the opposite of that. So, programmers like their memory to be abundant, cheap, and non-volatile, but this isn't possible, so instead we just use different forms of memory for different purposes. So, inside your computer is at least 3 different forms of memory, and they are the following. At the very top of this memory hierarchy, and yeah, all of the different forms of memory that is in a computer, they form a sort of pyramid. So at the very top, we have registers. These are the fastest forms of memory available on the computer, but here's the catch. They are part of the CPU itself. You cannot go to the store and buy a register. Also, if you go to the store and buy a register, the store owner is gonna be confused, like, cash register? Is this a robbery? No, like a register of a computer. Eh? So at the very top we have registers. Fast, but small and expensive. They are part of the CPU, and they can only hold 1 word each. What is 1 word? Well, for our purposes, 1 word is going to be either 32 bits long or 64 bits long, depending on the architecture. So it can only hold 1 word of memory. That's it. But it's important for the computer to hold these things in memory because, well, there are all sorts of registers in the CPU and they all hold all sorts of things. One register could be holding a memory address, another register could be holding the result of an addition operation, and then another register could be holding, for example, what instruction are we at in the program? So we could be at instruction 6600-42, and the register, there are several registers, and one of them would be holding the current instruction number in the computer, telling the computer we are at this step in the program. So registers are used for all sorts of things, but they are all exclusive to the CPU. Below that, we have random access memory. When we think of memory on a computer, this is probably the memory that you're thinking about. We call it RAM for short. But for our purposes, I'll call it main memory. Slower than the registers, more abundant than the registers, but it's also volatile. Oh, by the way, the registers are also volatile. Anything stored in them, it's lost when the CPU powers off. What doesn't get lost when it's powered off is whatever is stored in secondary storage. So anything that you store on a hard drive, that's gonna persist even when you turn off the machine. That's However, secondary storage is even slower than random access memory. So when it comes to the CPU trying to access stuff, trying to access data, registers are going to be the fastest. And then after that, it's going to try to access random access memory, which is slower. To access stuff from secondary storage is even slower, but here's the catch. The CPU is unable to access anything in secondary storage directly. It's up to the rest of the system to load files from memory, or programs from memory, no, programs or files from secondary storage, and then put them into memory. Only then will the program be able to read what was in secondary storage. Though that hierarchy was a little bit incomplete because there are a few more levels than that. Cache, for example, is basically a form of memory that lies between random access memory and the registers. Basically, to access random access memory, to access main memory is slower, but we can give the system a speed boost by caching some of the most frequently accessed stuff in main memory. So cache stores these frequently accessed things, with the idea that if the computer wants to access something from memory, it checks the cache first to see if it's there. And if it's there, we have a cache hit. That means the CPU just saved a lot of time accessing stuff from memory. By not going there, it just went to the cache instead. If it's not there, then it's going to take the extra time to, well, read it from memory instead. We generally divide secondary storage into at least two tiers of storage now. The first one is non-volatile memory devices, basically solid-state drives. And you probably have one of these in your system right now. Basically, a form of storage that has no moving parts. It is a bit more expensive than hard disk drives, which is what we probably think about when we think about secondary storage. NVMe devices are more expensive, but they are faster in many cases. Hard disk drives are cheaper, but they have a risk of failure because of all the moving parts inside. I also included removable storage. That includes flash drives, optical disks, and at one point floppy drives. So, once upon a time when personal computers was still in its infancy, hard drives were so expensive that it was expected that if you wanted to save anything on a computer, you would do so by saving it to a floppy drive. In fact, you were given two floppy drives. On Windows systems, at least, these were drives A and B. They were for floppy drives. When the cost of hard drives dropped to the point where it was common to have drives of tens of gigabytes on the computer itself, the floppy drives were done away with, but the drive letters that they were assigned to were still kept. And it is for this reason that to this day, on Windows systems, the very first drive that is given a drive letter, it's given the drive letter of C. A and B were reserved for floppy drives. Why does the major scale start at C? Because A and B were reserved for floppy drives. That is a pun that makes sense in the context of conflating drive letter assignment and music theory. Anyway, that is the memory hierarchy. So, in terms of how much these things can store, as I said, registers can only hold like one word each, 32 or 64 bits. Cache can only hold a few tens or hundreds of megabytes. Random access memory, main memory, is on the order of a few gigabytes or tens of gigabytes. Non-volatile memory is on the order of hundreds of gigabytes to a few terabytes, and so is hard disk drives. And removable storage, the size of that varies a lot. So, we're mainly going to look at this level here. We're not going to look at this level or this level yet. Not for a while. That's probably going to be more in the realm of CSE-4610. So, the part of the OS that manages the memory hierarchy is the memory manager. Its job is to efficiently manage memory. This includes allocating and deallocating memory to processes. The memory in question is main memory, or random access memory. This does not include secondary storage, which, as I said, that is its own thing, and we probably won't get to it at all in this class. That is probably something for CSE-4610. So, how do we manage this memory? Well, we're going to talk about something called a memory abstraction. But before we get to that, we have to talk about the absence of a memory abstraction. Because the earliest computers never had a memory abstraction. This means if a computer were to access some address, call it address 28, it is accessing that physical address in memory. Thus, the memory model presented to the programmer was simply physical memory. Physical memory has addresses that range from 0 to some maximum value. And each address corresponded to a cell that is usually 8 bits wide. When we say that something is 8 bits wide, these days we call that a byte. And a byte is assumed to be, well, at least these days, 1 byte is assumed to be 8 bits. So, let me repeat that. When programmers were working with memory in these early computers, they were directly working with physical memory. If a program were to write to address 28, it is going to write something directly into physical memory address 28. So here's the next thing. What if you wanted to run more than one program at once? Well, you can't. What if 2 programs are writing a value to the same memory address? Well, and the answer to that was simple. You simply were not allowed to run more than one program at once. Even if you somehow could, both programs would crash. You could circumvent this issue by having a multi-threaded program, but that wouldn't work if you wanted to run 2 unrelated programs at once. Like right now, I'm running PowerPoint and OBS. If this was a computer back in the day, this would be an impossible task. So basically, the idea is this. We can only run one program at a time. Or can we? Despite this, there were a few memory options available based on where in memory the OS and device drivers were stored. So we could run multiple things at once, but it's usually just gonna be the OS and maybe some drivers, and then the program, whatever program the user wanted to run. So only one process could run at a time. The user types some command that executes a program, and that program is loaded into memory. Once that program stops running, the user is prompted to run another program, and that overwrites the previous program that is in memory. Okay, but what if you really wanted to run 2 programs at once? Couldn't we just save one program and then load the other? And yes, this is what we're actually gonna get to in a little bit. This is called swapping. When you have a program loaded into memory, if you wanted to load another program, all you gotta do is save that first program, store it somewhere, say in secondary storage on a hard drive, and then you can load in the other program. If you wanted to load that other program back, you have to unload that program, put it into secondary storage, and reload that program. Keep in mind that we are not just rerunning the program. We are saving the state of the program. So these programs take up space in memory. We are saving the state of that memory. If you wanted to run a program while a different program is running, the memory contents for the currently running process, that is saved to the disk. So it's not like we're restarting the program all over again. We are saving the current state of the program. So if this was a video game, for example, of, say, Pong, the current state of Pong, that is saved and then reloaded when it's needed. We'll get to that. We'll get to more in a little bit. If we add special hardware, then we can actually run more than one program at once without swapping. The IBM 360 is an example of such a device that did this. So here, memory was divided into 2 kilobyte blocks, each assigned a 4-bit protection key. These keys are held in special registers in the CPU. A machine with 1 megabyte of memory therefore needed 512 keys, and that was just based on basic multiplication of 2-bit whatever. Since one byte is 8 bits, and memory was divided into 2 kilobyte blocks, we only need about 256 bytes of storage for the keys alone. The program status word also contained a 4-bit key. If a process tried to access a memory block without a protection code, if a process tried to access a memory block with a protection code that was different from the PSW's key, it would result in a trap to the OS, indicating an illegal memory access. And only the OS could change the keys, so a user process could not interfere with one another. So we're starting to get hints of how modern computers keep processes from messing up one another, though this implementation still had its own drawbacks. Assume 2 16 kilobyte programs are loaded into memory. Both begin running by performing some jump instruction. One program jumps to address 24. The other program jumps to address 28. So here, A and B, those are the 2 programs, but separately. But in C, we load both programs into the same area of memory. So in one section of memory, we have the first program. In another section of memory, we have the second program. You start to see the problem here. So in one program, the first instruction is to jump to address 24. In the second program, the first instruction is to jump to address 28. When we load both programs into memory, the first program says to jump to 24. The second program says to jump to 28. You would think it would be jumping to here, but no, it's actually gonna jump to the first program's memory. So when it says jump to 28, it's gonna go here and enter another program's memory space. So that's the problem. The issue is this. After the first program runs, the OS may decide to run the second program. The second program here is loaded after the first program. When it runs, it performs a jump operation to address 28, and that is part of the first program. If we had a way of keeping track of where the program is loaded, maybe instead of jumping straight from here to the first program's memory, we could just offset that value so it jumps to the correct value, which in this case is memory address 16412. Because in the previous slide, jump 24 for the first program is to go to here. Jump 28 in the second program is to go to here. But if the program were to be loaded starting at address 16384, when we say jump 28, what we really want to do is jump to 16412. So another hint of what the computer must do to make sure these programs don't accidentally mess with each other's memory spaces. So here's the problem with this setup. The 2 programs are using absolute physical addresses. So all we gotta do is we need some means of making sure that when one program tries to jump to some address, it doesn't accidentally jump into another program's address space. We gotta add some value to that so it jumps to the correct address. So as I said, we want some means of not jumping to address 28. We want to jump to address 16412. If done right, this relocation mechanism works, but it can slow down the program because now we have to do addition operations before we even jump to the right address. This can slow down the program. This is called static relocation, by the way. So the idea is this. A program is loaded starting at some address, and we save that in a register. When we try to do this jump instruction, instead of jumping to address 28, which is incorrect, it's going to jump to 28 plus whatever value is in that base address. So that's going to be 28 plus 16384, which means we're now going to jump to address 16412, not 28. And that's all you need to fix this problem of programs jumping into the wrong program. Most modern systems actually don't do this anymore, except for maybe systems in which they will only ever run one program. On such systems that are only ever running one program, say a smart toaster or a pregnancy test or a camera, they're only ever going to be running one program, so the idea of having a memory abstraction is basically moot. That hasn't stopped some people, however, from porting the video game Doom onto these devices. So there is this meta trend of porting Doom onto devices that reasonably should not play Doom. And that includes devices such as cameras, pianos for some reason, and yes, someone ported Doom to run on a pregnancy test. Look this up. You can't make this up. Anyway, that is how the first computers worked. They worked directly with physical memory. So when programmers wanted to write something to some address, they really were writing to that address. We don't really do this anymore, except for those few exceptions of devices only running one program, one specialized program made for the purpose of the device. No user programs allowed, unless you somehow port Doom to it. So, we went from having no memory abstraction to the notion of having what's called an address space. We want to have multiple programs running at once, but we need to solve two problems, and we've seen those two problems already. How to protect processes from each other, and because the memory also contains the operating system, we also want to protect the operating system from other processes. So we need to protect processes from other processes, and we need to protect the operating system from other processes. Also, we need a means of relocating memory addresses. So if a program says to jump to address 28, that needs to be translated to the corresponding physical address so it doesn't accidentally jump into another program's memory space. Although the solution presented in IBM 360 works, it doesn't solve the issue of relocation. We need something else, and that something else is the address space. An address space is basically the set of addresses a process can use to address memory. Each process has its own address space, independent of other processes' address spaces. Of course, the exception to this is shared memory. In shared memory, we have two programs, for example, that are sharing the same part of memory. They see it as part of their own address spaces, but they are sharing it between one another, so one process can write to this shared block of memory, say, hey, this is process 1 speaking, and process 2 says, I got your message, and then it writes in a reply. So an address space, much like physical memory, it starts at 0 and ends at some maximum value. So the notion of an address space, it would be like a block of cookie cutter homes. Everyone has the same floor layout of, say, the living room, but the idea of the notion of an address space is it's kind of like having cookie cutter homes. Everyone gets the same floor layout, but they have freedom to put whatever they want within the same space. So it is identical copies of the same space, but being used for different things. So, for example, jump 24 could be the first instruction in one space, but jump 28 could be the first instruction of some other space. Anyway, so we're gonna enroll with this notion of an address space. And here we go. So now we have what are called the base and limit register. To make sure each process has its own address space, we use something called dynamic relocation. So when a program is loaded into memory and it says jump to 28, it's not going to jump to physical address 28. Rather, the computer is going to translate that the sum. It's going to translate it to the correct physical address. So if a program were to be loaded in starting at address 16384, and we know how long the program is, the first thing that's going to happen is this jump 28 instruction. That 28 is added with the base register, and then it's going to be compared with the limit register. If that new address, 28 plus 16384, is within the range of the base register plus the limit register, then we are allowed to jump at that address. So the base register contains the address in which the program begins. The limit register contains how many addresses that program can access. So the base register is 16384 and the limit register is also 16384. That means the program starts at address 16384 and ends at address 3276. I don't know if that's a typo or what. My point is it's going to end at right before 32768. So that is the range of the whole program. It starts at 16384 and ends right before 32768. So that means if we do this jump instruction, we're going to add 28 to 16384, and we're going to see whether it's less than 32768. If that is the case, then we are allowed to jump. If somehow it screws up, if the program screws up and we're somehow jumping outside the memory space allowed for that program, then we have an illegal memory access that is a trap to the OS. Programs are loaded into a block of contiguous memory addresses. That's also another important thing. These are blocks of memory. It's one block per process. This also poses its own issues that we'll get into a little in a later bit. But they're not as well emphasized in this book as I expect. But anyway, my point is this. When we load a program into memory, it fills one contiguous block of memory. If an instruction says to jump to some address, say jump to address 28, the destination address is added with the base register to jump to some physical address within that process's address space. Simultaneously, that address is checked with the limit and base register to see whether that address was valid. That is, we are jumping to some address that is within that process's address space. If the address is less than the sum of the base and limit registers, it's valid. If not, it's invalid. The one little detail that I failed to add here is making sure that we don't jump to addresses below the base register. So that is also its own check. So we need to make sure that we are jumping to allowed addresses ranging from 16384 to less than right before 32768. If we add this to this and our address is within that range, we're good. Using a base and limit register is an easy way of giving processes their own memory spaces, because every memory address generated automatically has the base register contents added to it before being sent to memory. And some systems even protected the two registers so that only the OS could modify them, though not all systems did this. There is disadvantages to this, and that is the need to perform an addition and comparison operation on every memory reference. So if a program wants to jump to address 28, we need to convert that to the proper address first, and then we need to then we have to check whether that was a valid address. We need to do these two steps every time we want to access anything in memory. Comparisons are easy, but additions are slow unless you have specialized hardware needed meant to speed up addition. So yeah, that's the one problem with using a base and limit register. It may be slow. So now we get to swapping. In practice, we have more programs than there is space to fit all of them in memory. A typical system may create something like 50 to 100 processes right after booting alone. And many of these are just background processes. We call them daemons. Many of these are background processes that perform essential operations. They're called daemons, that is D-A-E-M-O-N. These are basically special background processes. So yeah. Demon in the sense of a supernatural being with no bias towards good or evil. Not in the modern sense of the word, meaning supernatural being inclined towards evil. So, a typical system may create like 100 different processes. Some of them are background processes. This isn't to mention all the other processes the user starts up afterwards. Some of which may use like several hundred or maybe several hundred megabytes or several gigabytes of memory. So some of the programs that we run these days are like memory hungry. So there are two general strategies to keep all these processes loaded: swapping and virtual memory. We're going to look at swapping first. We'll look at virtual memory in a little bit. Swapping consists of moving entire processes between memory and the disk. If a process is idle, that means it's not doing anything. Why do we need to keep this in memory? We can just unload it, store it on the disk, and then now we've freed up space that we can use for another process. If that process becomes active again, we can just swap out something else and swap in that now active process. So that is the basis of swapping. We take these processes that are in memory and we move them between the hard disk and memory as needed, based on how active or inactive these processes are. Virtual memory is where it's swapping plus paging. So virtual memory is based on swapping plus paging. Basically, you are running programs, but you don't load the whole program at once, and that is something that is really neat. But I want us to get to swapping first. When a system starts up, the memory initially contains the OS and any background processes that are started up alongside it. So here we're going to assume that the operating system is at the bottom end of memory, and now we have process A. As new processes are made, they're loaded into memory. If a process is idle, it is unloaded from memory and saved on the disk. This frees up space for new processes. If an idle process becomes active again, it's moved from the disk back into memory, possibly at a different location from where it previously was at. So we have the OS and process A, and then process B gets added, and then process C gets added. And process A just became inactive, so we can just unload that and free up space for a new process, process D. And process B, it looks like that terminated, so we can free up that space. And process A has just become active again. Let's find a space for that. Okay, that block of memory between process D and C, we'll just squeeze in process A in there. So as processes come and go, they're going to be moving around a little bit, but they're also going to be leaving behind what are called holes. These are spaces in which we can load new processes in. So this memory space is being occupied by both processes and unoccupied by processes coming in and out of memory. So these are called holes. The one thing about these holes is that they may be scattered all across memory, because as processes come and go, they will basically cut up this memory space into smaller and smaller pieces. This is not really mentioned in this part of the book, but this is called external fragmentation, and it can become bad in that if memory becomes too fragmented, then it means that there is no one space big enough to fit a process that we need to have loaded into memory. There is a way to solve that, and that is called memory compaction. where we shift all these processes so that they're on one end of the physical memory space. So that way, all these holes just bubble up to the other end of the physical memory space. This effectively combines all these little holes into one big hole. This isn't done all that often because this requires a lot of CPU time to, well, move everything. Processes are allocated some amount of memory that is determined by the operating system. If the size is fixed, then the OS allocates the exact amount of memory a process needs. If the size is not fixed, then that is, the process can grow. Then it may cause some issues. If a process is adjacent to a hole, there is some space next to it, then it might just be able to expand into that hole until it runs out of space. If, on the other hand, a process is sandwiched between two other processes and it needs to grow, then suddenly that process is not allowed to grow because there are two other processes in the way. How we resolve that, there are several ways. We can move one of the processes out of the way, or we can move the process that's trying to grow out of the way into a larger hole where it has more space to expand. If another process needs to be moved out of the way for a process to grow, but there's no more space on the disk, then we suspend the growing process in the meantime until there's more room available. Or, in the worst case, we just kill the process. If it is expected that a process will grow, then it's a good idea to allocate more space than they need to account for that growth. This reduces the overhead associated with moving processes out of the way, but this can result in wasted space if it turns out that the process never ends up growing. So we have wasted space from when processes move in and out of memory and fragment the available memory space into lots and lots of little holes, but we also have wasted space from when we allocate extra memory to these processes and they don't use it. That's called internal fragmentation. So here we have room for growth for these two processes here. So this part is actually in use, and the process is allocated a little bit extra memory to account for that growth. If process B here never grows, then we've allocated this block of memory for nothing. But if it does grow, then I'll just use up that extra space as needed. When it comes to swapping a process between memory and the disk, only the parts of memory that are in use are swapped. We don't swap the parts of memory that are not in use. So it would be inefficient to include this shaded yellow area here when we do our swapping. No. We only swap this part. Different parts of the program can grow. In the textbook, these are the stack and data segments. Some textbooks differentiate the data into even more pieces than that. In the other operating systems textbook that I call the dinosaur book, because it has a dinosaur on the front cover, that book talks about 4 parts, 4 pieces in the memory space of a process. This book only talks about 3. So in the Carnival book, that is the book that we're using, we have 3 parts of a program when it comes to what is in that process's memory space. Those are the program itself, the data, and the stack. The data and the stack grow towards one another. And between those two, that is the room for growth. In the dinosaur book, that is further differentiated into what is called the stack and the heap. The data segment, that is its own thing. The data segment is basically global values and other values. But the point is, the size of the data segment here is fixed. The size of the heap is not. So that would be, for example, dynamically allocated memory data structures. for dynamically allocated memory. The stack is used for keeping track of where you are when you are calling functions inside of functions inside of functions. So the stack is there to keep track of where you are in this chain of functions calling functions. The heap is there for memory that is dynamically allocated. And they grow towards one another. If there is no more room for either the stack or the heap to grow, then the process is moved somewhere else where it can grow. The process is swapped out of memory until room becomes available, or at worst, we just downright kill the process. So now we were talking. So far we were talking about how these processes are loaded into memory. So now we have. So as if you recall, processes are moving in and out of memory, and they are leaving behind holes. These are areas of free memory that can be used for other processes, which at worst may be too small to hold a process at all. There are several ways to manage that unallocated memory. We're going to look at two of them. Those are the bitmap and the free list. There are other methods that we'll probably never get to until, say, around CSE-4600. Those include the buddy system and something called slab allocation. So let's first look at that bitmap. With a bitmap, we divide memory into units of allocation. So we divide memory into small units ranging from a few words to a few kilobytes. Each unit is associated with a bit in a bitmap, indicating whether that unit of memory is free or in use. So we're going to ignore this chain here for now. We're just going to look at A and B in the diagram. So check this out. Process A is occupying 5 units, and then following it is 3 units of empty space. And then process B takes up 6 units. Process C takes up 4 units, and then there's 2 units of unallocated space. Process D takes up 6 units. That is 6, right? Yes, that is 6. 6 units for D, 2 units for E, and then so on and so forth. We keep track of those used and unused segments of memory using a bitmap. So 1 says that, so 1 is that unit of memory is in use. 0 is that unit of memory is free. So B is a bitmap. So we have 8-bit words describing how each section of 8 units is being used. So for the first 8 units here, that is 5 units used by A, 3 units unused. So the bitmap for those first 8 units is 111111000. From here we have processes B and C. Those are taking up 6 units and then 4 units. Though this unit is 8 units long, from 8 to 16. B is taking up 6 of those units, and then C is taking up 2 of those, and then it takes up 2 more in the next 8 sections after that. Well, even though it's only taking up like 2 units. So from 8 to 16, that bit sequence is 1111111. And then from C to part of D, that is 11 and then 00 and then 1111, and then D continues in the next. D continues from there, and then E, so that's 111111000. So my point is this. Sometimes processes can straddle the border between these bit sequences here. So part of C is described on this line and this line. Part of D is described on this line and this line. So processes may straddle the border between these 8-bit sequences, or possibly straddle several borders. So this bitmap here is organized into groups of 8 bits. So here's the thing about a bitmap. We are cutting up memory into units of all the same size. The size of that unit becomes an important design issue. If we make the size of that unit small, that means we are cutting up memory into lots of little pieces. This means to keep track of all these pieces, we need a larger bitmap. Conversely, if we make the size of the unit large, there are fewer units to keep track of, therefore we need a smaller bitmap. So how large your unit is affects the size of your bitmap. How much information do you need to store the bitmap? So this is something like 16 units. If I cut them up into smaller units than that, this is, I believe, 32 units. That means we need this means here we need 32 bits to store the bitmap for this. This one needs 16 bits. So yeah, the larger you make your unit, the less space you need for your bitmap. And conversely, the more units you have, the smaller the units are, the more space you need for your bitmap. A bitmap provides a simple way to keep track of memory words in a fixed amount of memory because the size of the bitmap depends only on the size of memory and how big your allocation unit is. The main problem is finding space for memory that requires some number of units, call it k. The memory manager must then find k consecutive zeros in the bitmap, indicating k consecutive units of free memory. This is a slow operation because you have to go at the beginning and then go straight to the end, looking for some sequence of k zeros indicating, hey, we have free space here, let's put our process in there. This itself is a slow operation, and this is an argument against bitmaps. So what can we use instead? Well, another way of keeping track of memory is to maintain a linked list of allocated and free memory segments, where a segment either contains a process or is a hole between two other processes. So now we're going to look at part C of this diagram. This is our linked list. So previously we were using a bitmap to represent used and unused sections of memory. We're using a bitmap instead. No, we're not using we're using a linked list over a bitmap instead. So here's how it works. Process A starts at address 0 and takes up 5 units. There's a pointer to a hole that starts at 5 and spans 3 units. And then that has a pointer to the next process, which starts at 8 and spans for 6. That has a pointer to the next process, which starts at 14 and spans for 4. That has a pointer to the next segment, that is a hole. It starts at 18 and runs for 2 units. That has a pointer to the next segment, that is a process, that starts at 20 and is 6 units long. It has a pointer to the next segment, that is a process, it starts at 26 and runs for 3 units long, and then it continues to the next segment, that is a hole. It starts at 29 and runs for 3. That is our linked list. And this is a different way of conveying the same information that this is conveying. So, 2 different ways of representing the same information. In such a list, each entry in this list specifies whether the segment is a process or a hole. That segment states where it starts and how long it is. There are a few rules to this linked list, by the way. The segments in the list are sorted by address. This makes it straightforward to update the list. A segment that is a process will always have 2 adjacent segments to it, unless it's at one of the ends of memory, in which case it'll only have 1 adjacent segment. Holes that are adjacent to other holes will combine into 1 hole. for ease of merging, you really should be using a doubly linked list, not a singly linked list as shown in the diagram previously. So, this means there are 4 ways a process can be adjacent to 2 other processes, between 2 processes, between a process and a whole, and there are 2 ways for that, and between 2 wholes. If a whole is adjacent to another whole, it'll just combine. They'll just combine into one whole. So really, there's only one way in which a whole can be adjacent to other segments, and that is between 2 other processes. Because if it's between a process and a whole, or between 2 wholes, those wholes will just merge. So, if we have some process X, but sandwiched between 2 processes, when it terminates, it's gonna leave behind a whole. If it was between a process and a whole, when process X terminates, it's gonna leave behind a whole that merges with the whole next to it. And finally, if process X was between 2 wholes, when it terminates, the whole it leaves behind merges with the other 2 wholes next to it into one big whole. So those are the rules. Processes leave behind holes and they merge with other holes, if there are holes next to that hole. With these processes and holes sorted by address, we can use one of several algorithms to allocate memory for a created process, or a process that's being swapped from the disk. The first of these algorithms is called first fit. Find the hole that is big enough to fit the process. The remaining space becomes a new, smaller hole. So we have these holes in memory, and those are holes in which we can shove in a new process. This may leave some leftover space that becomes a new hole that we can use for another process, or it can merge with another hole if another process next to it releases its memory. A variant of first fit is called next fit. The location of the hole created by first fit is saved, so the next time we try to search for a hole, we start at that previously made hole. We don't start from the beginning anymore. A well-known and widely used algorithm is called best fit. Find the smallest hole that is just large enough to fit the process. The idea behind best fit is to leave behind the smallest possible hole. We can also contemplate the existence of the opposite of best fit, called worst fit. The idea behind that is to maximize the size of the leftover hole. Find the largest hole in which a process can fit, put the process in there, and the leftover hole is as large as possible. We can use that for more processes. In terms of performance, simulations show that next fit is slightly worse than first fit. Best fit is slower because it requires searching the list every time a hole is needed, and best fit tends to fill up memory with lots and lots of tiny useless holes. In comparison, first fit creates larger holes on average. This can be a good thing or a bad thing, depending on how bad fragmentation becomes. This text doesn't really emphasize external and internal fragmentation, not to the same extent that the dinosaur book does, but if you have lots and lots of tiny holes, that is external fragmentation. Not good, because now those holes are way too small to fit a process. But that's why we perform compaction. That is where all the holes are combined into one big hole again. All 4 algorithms can be sped up by keeping separate lists for processes and holes. For even more performance gains, the list of holes can be sorted by size. So the largest or smallest hole will be at one end of the list. To find the largest or smallest hole is as simple as accessing the beginning or the end of that list, depending on what we're looking at and depending on the sorting order of that list. If holes are sorted by size, first and best fit are equally fast, and next fit is pointless. The lists for processes and holes are kept in memory, but another optimization is to store hole information in the holes themselves. The first hole contains a data structure containing how many units large the hole is, and there's a pointer that points at the next hole. that next hole has its own data structure that says this hole is this many units large, and then has a pointer to the next hole, and so on. So basically, these data structures are being stored in memory, but we're using the holes themselves to hold information about the holes. That's kind of funny, don't you think? You're using the holes to store information about the holes. There's a fifth algorithm, by the way. That is called quick fit. Here we have separate lists for the most commonly requested sizes of holes, like 4 kilobytes, 8 kilobytes, 12 kilobytes, and so on. To find a hole of a specific size is extremely fast, but it has a disadvantage. As the same with all schemes that sort holes by size. When a process is terminated or swapped, finding the holes it can merge with is expensive. And the reason why we do this merging is as follows. If we don't merge, memory can fragment to the point where no processes can fit into any hole. That is external fragmentation. We do not want that at all. Okay, so now we're gonna get into virtual memory. Here's where things get interesting. Even with base and limit registers and managing holes, there is still one issue left to resolve. The fact that over time, the size of software has also grown. When this textbook was published, Windows 8 was fresh off the block, and it had a memory requirement, a minimum memory requirement of at least 2 gigabytes. The memory requirements for Windows 10 aren't too far off from that. Windows 11 has now came out and has been out for a good while now, and it has a memory requirement of 4 gigabytes of memory. For reference, 32-bit systems can address a maximum of 4.2 billion unique memory addresses. That corresponds to 4 gigabytes of memory. That means if you can run Windows 11 on a 32-bit system, it will use up the 4 gigabytes of memory and have nothing left for any other programs, period. This is resolved by Microsoft saying that Windows 11, there is no 32-bit system. There is no 32-bit Windows 11. It's only 64-bit. This is interesting because this is the very first Windows operating system in which you only have the 64-bit version. There is no 32-bit Windows 11 at all. Also, as a public service announcement, it is 2024 as of the time I am recording this. Windows 10 support will officially end next year. That is 2025. I'm saying this now because you gotta get ready for when that happens. It's been a good run, Windows 10. Even with all the controversies that you have. But yeah, that means any older hardware that you might have, it's just gonna fall out of support now. Then again, that hasn't stopped some people from using Windows XP for special applications. So maybe we'll find. My point is, prepare and adapt, maybe. Getting back on track, regardless of the forward trend of operating systems and programs in general requiring more and more memory, we still have the issue of making space for all of these memory-hungry programs, in addition to running several programs at once. So, how do we make space for so many programs that require so much space? Well, here's the neat part. You don't. I'll explain what I mean by that in a bit. So, here's the problem with swapping. We are limited by how fast we can write stuff to the disk and read stuff from the disk. We are limited by the transfer rate of our hard disk drive. The larger the process, the more time it takes to transfer. So, what if we could just cut up this program and... So, a hint of a solution can be found in what was done in a few early systems. One of the first solutions was to split the program into pieces called overlays. Such a program would only use one overlay at a time, and an overlay manager would load the next overlay when it was called for. The use of overlays, however, was not without problems. The problem is, well, cutting up the program into pieces was time-consuming, boring, and error-prone, and not to mention, very few programmers were even good at cutting up programs like this. So surprisingly, or maybe unsurprisingly, the solution to cutting up programs is to just automate the process. Have the computer cut up the program itself. This would be known these days as virtual memory. Here's the basic idea of virtual memory. Oops. The basic idea of virtual memory is to have each program have its own memory space. So every program has its own memory space. That was also the same thing when we were doing swapping. But now, that memory space is cut up into pieces. Those are called pages. Each page is a contiguous range of addresses. Also, each page is the same size. All pages are the same size. That's the other thing. So, every program has its own memory space cut up into pieces. Each page is a contiguous range of addresses. Each page maps onto physical memory, but not every page needs to be loaded into memory. When the program references a part of its address space that is not in memory, the hardware loads that missing piece and the program tries again. So, most virtual memory systems use a technique called paging. When a program executes an instruction, say move register 1000, it generates a memory address. In this case, we're moving the contents in address 1000 to a register. This generated address is a virtual address, and these addresses form the virtual address space. These addresses don't go straight to the memory bus, not yet at least. Instead, they go to a memory management unit where they're translated from a virtual address to a physical address. Because the hardware can only work in terms of physical addresses. The programs can only work in terms of virtual addresses. The MMU converts one address of one form. The MMU converts addresses of one form to another. Virtual memory is broken into pieces called pages, which are all loaded into physical memory. All pages are the same size. So these pages are loaded into these pages are loaded into physical memory. But the key thing is, we don't need to have all of them loaded at once. Physical memory is also cut up into equivalently sized pieces called page frames. Each frame holds one page each. So here's the neat part. When a program is loaded, we only load the parts of the program that are needed. And that is the neat part. When we load a program, we only load the parts that we need. If, for example, we need to load some other part of the program that isn't there, then the system will simply just load the missing piece. Only the pages that are needed are loaded, reducing the amount of memory needed for a program. Pages can be mapped to page frames in any order, so any size constraints that were imposed to us by swapping no longer apply. This also means a program can be loaded into memory in pieces, so it's no longer the case that we have contiguous memory for our program. It can just be in pieces all across memory. Also, because of the above point, because pages can be mapped onto page frames in any order, memory allocation does not need to be contiguous anymore. If a process needs more memory and it can't grow because there are processes in the way, no problem. It'll just continue somewhere else, and that's also part of the process's memory space. As far as the process is concerned, it's seeing a contiguous virtual address space, even though in physical memory it may be cut up and incomplete. Check out page 2 in this program. It's labeled with a 6 because it's loaded in frame 6. Its virtual address space consists of the addresses from 8192 to 12287. It is currently loaded into a page frame corresponding to physical addresses 24576 to 28671. As far as the program is concerned, when it works with page 2, it sees the virtual addresses 8192 to 12287, not the physical addresses 24576 to 28671. To the program, when it sees address 8192, it only ever sees it as address 8192. To the hardware, however, when the program says address 8192, that is translated by the MMU to physical address 24576. Also, you may have noticed one thing. The fact that the virtual address space is larger than the amount of physical memory. Specifically, we have 8 pages of the program loaded into physical memory, but the other 8 pages are absent. Where are they? We'll get to that in a little bit. In hardware, we have a present absent bit used to keep track of which pages are in memory and which pages are not in memory. So what happens if the program tries to access virtual address 32780? This address is part of page 8, which starts at virtual address 32768. This is a page that is not loaded into memory. So what happens? Well, the program's gonna try to load the stuff from that page, and it's going to result in a trap to the OS known as a page fault. So it tried to access something that wasn't loaded, and the program just flat out stops. So the program broke. Now what? Here's what happens next. So the program stops running, and it triggered what's called a page fault. The operating system realizes, oh no, a program just tried to load something that doesn't exist. I gotta go fix it right now. What the operating system does is it goes and finds that missing page. Let's just say that missing page is on the disk. So it goes to the disk and makes an I/O request to load that missing page. At the same time, it also makes another I/O request to unload another page that is loaded into one of the page frames. However, it must make a decision. Which of these 8 pages that are currently loaded into a page frame, do I take out so I can make room for the missing page, page 1? Let's just say, for the sake of example, it's going to pick out frame 1 that contains page 1. It's going to page out page 1 and put it on the disk. Meanwhile, it makes an I/O request to load page 8 into that now freed up page frame. So now we have page 1 no longer in memory and page 8 loaded into memory. We also have to have the MMU change the 2 pages present absent bits to reflect these changes. So basically, what happened was we swapped pages. We find a page frame containing a page that has not been used for a while, and that is its own thing that we'll get to in a little bit. We unload that page, so we free up that page frame for the page that we want to load. That page is loaded, and now, whatever it was the program wanted to access, it is now in memory, so we can simply restart the program at the exact place right before it triggered the page fault. So if the program was trying to access address 32780 and it couldn't, the operating system basically gets the program to try again. Now that it sees the page has been loaded into memory, it can proceed as normal. So if the program needs to access something that isn't loaded yet, the operating system will simply unload an underused page and make room for the page that is needed. And that's how it works. That is how paging works. Basically, as pages are moved in and out, we swap pages as needed as the program requests them. Let's look closely at one of those virtual addresses, by the way. Let's pick out one of them, address 8196. Because we're dealing with a 64K memory space, this means we have 65,536 unique memory addresses. That is something that we can express as 16 bits because 2 to the 16th power is 65536. Address 8196 is simply just a 16-bit unsigned binary number that expresses that value. And we have it right here. Each page has 4,096 addresses, and there are 16 pages. If you do the math, 4,096 times 16, that is 65,536. Since 2 to the 12th power is 4,096, we can use the lower 12 bits to be used as an offset in the page. Where in the page are we looking at? The upper 4 bits, that is 4 bits, and 2 to the 4th power is 16. We can use the upper 4 bits as a page number. What page are we looking at? Address 8196 corresponds to page 2, offset 4, or the 4th address of page 2. Also keep in mind that these pages are 0 indexed, so there's a page 0 and there's an address 0 as well. Basically, all counting starts at 0 here. Also keep in mind that none of the rules that we were talking about here are not unique to base 2. If we were instead working with base 10 addresses, the rules are the same. So say we have some decimal address, 103714. The first 3 digits are the page number, and the last 3 digits are the offset. So address 103714 simply means page 103, offset 714. With 3 digits each for the page number and offset, this means we have 1 million unique addresses spread over 1,000 pages. So, the page number is used as an index in a page table. The page table is basically a lookup table that converts page numbers to corresponding page frames. Basically, where in physical memory is this page loaded? So, this page here, that is page 2. It is currently loaded in page frame number 6. That's why it's labeled 6 here. Don't get confused with these numbers here, because this is a frame number. This is page 2 that is loaded in frame 6. Don't mix them up the same way that I mixed them up. In fact, I have to go in and fix up the slides because I did screw up the numbers. So with address 8196, this is page 2 offset 2. Page 2 is loaded into frame 6, thus this is frame 6 offset 4. As a physical address, this is address 24580. For reference, if you want to convert a page number and offset into an address, multiply the page number by the number of addresses per page, and then add the offset to that. Given that our pages are of size 4096, virtual page 2 offset 4 is 4096 times 2 and then plus 4. Because page 2 corresponds to frame 6, the physical address is 4096 times 6 plus 4. With the decimal example from a few slides ago, that is page 103 offset 714. That is 103 times 1000 plus 714. Or better yet, because these are in decimal numbers, all you gotta do is concatenate the two. So 103 concatenated with 714, that is our address. The computer works with base 2, so everything is going to be in base 2. That may be a little bit confusing, but keep in mind that if somehow computers were working with a decimal, it might be a little bit more intuitive that way. There's nothing special with base 2 or base 10, except for the fact that it's just easier for the computer to differentiate between 2 voltage levels. That's why all our computers are in binary. Okay, so that is swapping and paging and how computers operated without a memory abstraction. So yeah, this is everything that I wanted to cover for today. However, we will be covering more about Chapter 3 in a little bit, so there are some caveats that you'll want to keep in mind. There are several ways to organize the page table. It's the page table that converts page numbers to page frames. The page table says, hey, this page that you're looking for is in this frame over here. It also says, hey, this page you're looking for, that's not loaded into memory right now. There are several ways to organize the page table, as well as considerations regarding the page table size. The size of the page table depends on how big we make the pages. Also, when we had the program here, take out page 1 and load in page 8. We need an algorithm that the operating system can use to decide, okay, which page do I move out of the way to make room for this other page? When a page frame is selected to load a missing page, that frame should ideally contain a page that hasn't been used in a while, or better yet, contain a page that the program will never use again. So yeah, there are algorithms that we can use to determine which page frame to select if we need to load a missing page. We need to find a page frame whose page we can unload so we can load in the missing page. So yeah, those are the caveats that we need to keep in mind for when we continue with Chapter 3. That's going to be it for now. I hope you learned something new about all this. Hopefully it's all pretty simple. Paging is actually paging plus swapping, because we are swapping pages. Originally, the term swapping meant the idea of swapping entire processes, except now we have these days swapping and paging, where we are swapping parts of processes. So we're going to continue our discussion hopefully this Friday, and at worst next week. We're gonna look more into paging, and I'm gonna say right now that this is probably gonna be the last big topics that we'll be covering for the class. If I give you any homework assignments, it's probably just gonna be translating addresses from the virtual memory space to a physical memory space. And for ease of practice, I might give you both binary and decimal examples. So with that, I'm gonna end the video here, and then we're gonna continue with our next part of Chapter 3, hopefully as early as this Friday, and if not, next week. Alright, take care.